Hello, this is Professor Khan, and this is week 2 of Heat System Design, EST-204. And this week we are covering chapter 1 in the book, Residential Energy by Kruger. And this week is going to be Principles of Energy. There's a lot of information in this lecture, so please try to read the book so you can have some kind of cross information between the PowerPoint and the book. And also the recording is going to be posted on Blackboard, so you can pause and rewind and let me know on the class meeting if you have any questions. So this week we will, let me check this. We will describe energy, define what is energy, and define the field of thermodynamics. I know the word thermodynamics can be a little bit involved and intimidating, but it's basically the branch of physics that describes and studies the heat relationship with movement and heat energy. Also explain the first law of thermodynamics, the second law of thermodynamics. They're very simple, probably you already know them. You're just putting them in physical form. Again, using the physics language. We will define latent and sensible heat and give some examples, and also identify the use of the term enthalpy. So, first law of thermodynamics, second law of thermodynamics, what is latent and sensible heat, and what is enthalpy. So 5 things, if you master them this week, I think we have achieved our goals. Okay, let's start. So first of all, what is energy? There are so many definitions of energy, and I'll try to explain it as simple as possible. So energy, in my perspective, is the ability to do work, and work can be defined as displacement. So energy is the quantity of power, and power is how fast do we spend energy. That's how I understand energy, and I hope that will be simple enough. So energy does not come from nothing. It's always a source. It always changes form from one type of energy to another. It could be heat. Heat can change into mechanical. It could be stored in a form of food, fuel. So it does not vanish. It will always be accounted for. The entire energy of Earth is conserved. Earth receives energy from the space, and there's energy in Earth that always transforms from one form to another. If you burn a stick of matchstick, probably the energy in that matchstick came from the powder, the gunpowder in it, uh, whatever chemical is in it, and the wood, which is the fuel. The wood got its energy from the tree got the energy from the ground and also from the sun, and eventually we can relate our energy coming to the sun. So if you see sun, tree, match, burnt. So what about after we burn the match? Where does the energy go from? It transformed into heat. It transformed, some of the material transformed into ashes, and everything can be accounted for. Nothing get destroyed. It just transforms from one form of energy to another. Some of them are useful to us, some of them are not. So I hope that makes sense. It doesn't vanish, and I'm sure at some point you have heard of this law, the conservation of energy. It's exactly what what we just said, that energy does not vanish, it's always there. And scientists has been tracing energy, all the energy in the universe from the Big Bang or the beginning point. So again, keeping that concept, even though it's so vast and so big, into simple form is still there. If you burn a gallon of fuel in your basement, that energy should be accounted for. Some of them are losses, some of them transfer, some of them become heat, and some of them become gases. So having that mentality will enable you to know and account for all the energy that you have spent. And again, energy is related to finally money. You're paying for that oil. So it's very important to know where did it go, and where is it going, and what form it is taking. Okay, and that is actually the first law of thermodynamics, that energy does not get destroyed, it does not come from nothing, so it's a conservation of energy. So if I ask you what is the first law of thermodynamics, you can just say the conservation of energy. Energy does not get destroyed and does not vanish. Okay, energy is neither created nor destroyed. So it's a very vast physical question, but for our laws and simple physics, it does apply that energy does not vanish or come from nothing. So where does it go? Again, it transforms from one form to another continuously from now till the end of time. The sun got its energy from somewhere, and over billions of years it will go away to another form. Some of this energy is useful to us. We can utilize it, and some of them we can't. Like the matchstick, after it's burned, we can use the heat, but there's not a lot of uses for the ash, but will go to somewhere else. So that is also a good concept to keep in mind. I'll give you another example. Again, the sun powers plants. Plants makes food. We eat the food. There's calorie count for that. It's a unit of energy. My body keeps its temperature by burning energy. So the food transforms into heat, into chemical energy, chemical storage, then into heat, and that heat maintains the body temperature, and also other forms of nutrients goes to power the muscles. So again, if anybody goes to the gym and they're trying to lose weight, they always tell you about calorie count and how much energy you're burning. You go on a treadmill, it's basically burning how much energy you spend, because your body temperature goes up and your metabolism goes up when you're running, and again, it's a form of energy, and that's why you feel hungry after you do a lot of cardio. Okay, I hope this kind of simplifies the concept of energy, even though it's a very, very vast field. Forms of energy. So, say there's potential energy. What is potential energy? For example, if something has been elevated against gravity, so we follow the force of gravity to elevate something, so now it has potential energy, be it a ball, a rock. Once you let go of that energy, it will start moving and transform it to kinetic energy. Once it hit the ground, probably it will transform into noise, temperature, friction, and some of that also go to the material change. So again, it will convert from one form to another. In your car, for example, if you account for the energy that you're putting in your car, which is gasoline, that is chemical energy. Once you burn it, you get heat. The heat is transformed into mechanical energy. Some of that heat is lost, some of them is used to move the car. When you move the car, it will resist air, and that also uses some energy. And overall, 99% of our energy comes from the sun. So if you think about it, take a minute to think about that. Plant-based life forms, fuel, heat, light, all these are forms of energy coming to Earth from the sun. So all over the years that the Earth has existed, around 4 billion years, this energy came from the sun. So what about the 1%? The 1% of Earth energy comes from the ground, which is the Earth cooling off throughout the millions of years. So the Earth at some point was a melting rock. You still have molten lava inside, and that energy comes out from the Earth cooling throughout the years. Again, it's a very big, vast concept, just to get the idea of where energy comes from and where does it go. So measurement of energy. How do we measure energy? There are so many units, and they are all interchangeable. They can go from one unit to another based on the field. If you go to medicine, probably they're not going to use kilowatt. They will use calories. If you go into HVAC, we use BTUs. If you go into electrical equipment, they use watts. So there's always, and they all change. We can transfer that from one unit to another, but at the end it's the same measurement for the same quantity of energy. So we have therms, we have kilowatts, therms, pen, therms, kilowatts, which is very common. You will see those we can see volume of oil or gas, which is again a stored energy. So you can see energy as a volume, and even like body fat is volume of stored energy. So that's again 1 pound of body fat is 3,500 calories. Calories can also be changed into watts, so you can practically calculate how much wattage you have to spend to burn that energy. You can convert all forms of energy again to kilowatt, which is the standard. Watt is the standard. SI, which is System International for unit, but which goes back down again to Newton per meter, which is kilogram per meter per second square, if you want to go into the details of physics. But watt again is a form of energy measurement. So energy transferred, that means work done to move an electric charge from one coulomb through an electric potential difference of 1 volt. That's a measurement of energy of electricity. So energy measures are universal, it's just different name and different unit. I hope that makes sense, and you can look it up also and see what other names of energy. But at the end, it's always the same, and they can be transferred from one verbiage to another. Units, more units. We have BTU, which that's something we use in HVAC. It's BTU stands for British Thermal Unit. Again, we still use the imperial system in the US. The rest of the world uses kilowatts, and even in HVAC we still stick to BTUs because this is what it became known for. So we will keep that as our unit for heat. What is that? What about watts? So there's a conversion between watts and BTU, and it's 1 BTU is 3.4 watt. 1 BTU 3.4 watt. Okay, kilowatt is 1,000 watt. Makes sense. And we also have foot pound per minute. I don't think we're gonna use that, but you get the point. There's also here in the bottom you see, get that out, you can see it. Crop this is okay. Fine. If you see at the bottom, there's 1 horsepower, which is 33,000 foot-pound per second. Again, horsepower is another measurement of energy, and you will see that in industrial boilers. So probably if you are taking power plant, you will deal a lot with horsepower. It's just another easier way for large amount of energy. Okay, on. So for HVAC we use BTU. That's the most common one we work with, which is actually the energy in 1 matchstick. This is how they decided this is going to be our measurement. It's also the measurement to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So it's a very primitive definition at that time. It worked very well for us, and you know we used a lot of units based on the past scientist nomenclature. So it's good to know that. A therm is 100,000 BTUs. So again, probably you will see that in your energy bill. If you're paying for gas, they will charge you per therm, which is 100,000 BTUs. Okay, that sums up the idea of energy. Let's talk about what is thermodynamics. Thermodynamics is the branch of physics concerned with heat and temperature and their relationship to energy and work. And we said before that heat is energy, temperature is the measurement of heat. So please try to make that distinction. And energy is a quantity of ability to do work, which is displacement. So those two are also connected. Again, the first law of thermodynamics talks about conservation of energy, and we talked about the idea that the energy comes from the sun. Sun gives us energy. This energy is received and goes into living organism, being tree, grass, moss, animals, and so on. These animals fed on the sun product, and over time they became fossilized fuel. This fossilized fuel or regular fuel is turned into heat. We use heat to make work, and that work again comes out as heat and also some landfill because of byproduct. Again, go back to this matchstick. You're gonna use the heat, but you're gonna throw away the burned matchstick. As we go along and we talk about energy, we're trying to make the most out of heat, the useful energy, and reduce the waste. As we spend all the fossilized fuel, all the fuel we have in a high rate, we will not be able to match our demand. So our demand for energy is much higher than what the earth is supplying on a daily basis. Currently we're using our reserve for millions of years, but eventually we will reach the point where we have finished all the reserve and we have to have something that is renewable. So we can still use like biomass, we can grow our own fuel using corn, using oil, using ethanol, but something that you can produce on a daily basis using the sun. We can use the sun directly using technology to transfer sun into power or heat. So that being said, we are working on a lot of reserve, and it's time for us to correct that and work on something that we can get on a daily basis. Okay, it's like you're spending your saving right now, and at some point you're going to depend completely on your income, and you have to live on paycheck to paycheck, so to speak. Okay. Second law of thermodynamics, the easiest way I can describe that is simply in nature, heat always moves from high to low. That's actually nature's law. And so in the summer, the heat moves from outside to inside. In the winter, not the winter, sorry, heat moves from inside to outside. So the second law of thermodynamics means like heat always moves from high to low, and if you want heat to go from cold to hot, what do you think you should do? You are going to put an equal amount of work of that energy you want to transfer from cold to hot. So if you think of an AC, what does the AC do? The AC is actually reversing the natural law of thermodynamics. Is moving heat from cold to hot, because again, it's in the summer, it's 90 outside, it's 80 inside, but you want to be 70, so you're going to move heat from cold to hot. So you have to put energy. What that energy is going to be in BTU, so you need some BTUs into that AC, and that BTUs are going to be supplied using kilowatt with electricity. So I hope this makes sense. So this is half the law, that heat moves from high to low, and if you want it to move from cold to hot, you have to put in equal amount of energy, or sometimes more, depending on the efficiency of your system. Okay, so if we want to move heat from cold to hot, we have to again put equal amount of energy, and that's the complete law. So the law is heat moves from hot to cold, and if you want it to move from cold to hot, you have to put equal amount of energy. So if you want to move 1000 BTU from a room, we have to put in the equal amount of energy, which is either 1000 BTU per hour or 0.3 kilowatt. That's the energy equivalence of BTU. If you go and find out some energy conversion calculator on your phone or in Google, probably that's going to be the equivalent. So, and probably depending on how efficient the system is, you might have to put more than 0.3 kilowatt. So if you want to put heat in the room by 1000 BTU hour, either we can use 0.3 kilowatts, or you can also burn some fuel if you want to add heat, and that's the equivalent of 0.02 gallons of fuel oil, number 2 fuel oil. How did I come up with this number? So one gallon of fuel oil has around 135,000 BTU. And okay, I hope this recording still continues, because I'm trying to see what's kind of get discontinued. But anyway, what I was saying is that if you want to put in fuel oil, we say that fuel oil is fuel oil is 135. Okay, so if you have 135,000 BTU in 1 gallon, if you want to burn the equivalent of 1,000 BTU only per hour, you have to burn that amount of oil. So again, we can transfer energy from one form to another, and in this case, going to be a gallon of oil. Okay. So temperature and heat again. I want to emphasize that what is temperature and what is heat? They are different. Heat is energy, and temperature is how do we measure that energy. Could be Fahrenheit, could be Celsius, could be Rankine, could be what is the other one? Kelvin. So heat is energy and temperature is measurement. Okay, hopefully we get that done. What is enthalpy? It's the energy given by the temperature of a given weight of material. This is sorry, I did that. It's given by a temperature at a given weight of material. You don't have to know that per se. It just I want to explain to you in layman term that whatever energy is in the material is given by something called enthalpy, because you will see that in the psychometric chart, and if you were to design an AC, probably you will see that. So if you want to just make it simple, you can say enthalpy is the useful amount of energy that we can utilize, because there are some forms of energy you cannot use. So whatever energy we can use for us, that's going to be enthalpy. I'll go back to that other example of the matchstick. Whatever heat we can get from the matchstick is going to be our kind of enthalpy, just to make things a little bit easier. But enthalpy is the total energy we can get out of a fuel. So this is here is defined as the thermodynamic potential, designated by the letter H, that consists of the internal energy of the system plus the product of pressure. So don't worry about that a lot, but at least you know that enthalpy is the amount of potential energy in substance. And here we have the pressure is one part, specific volume, which is the inverse of density, and internal energy, and this is mass. Do you need to remember that? No. If you can just understand that enthalpy is another name for useful energy, that will be enough. Okay, we're not going to be physics scientists here. We just want to understand when we see enthalpy in the psychometric chart, what does it mean and how do we interpret that. Okay, moving on. Sensible and latent heat. This term is very, very important. I want you to focus and take a second to remember what does it mean. Sensible heat, I'll start with sensible heat. From the name, sensible is something you can sense, right? So, sensible heat is the heat that you're putting in that you can measure, you can feel. You can put a thermometer in it and you can see or feel the temperature changes. That is sensible heat. So if you're adding heat, you're heating water and you see the temperature rising, so you're adding sensible heat. That heat actually is raising the temperature. Sensible heat. Okay? On the other hand, we have something called latent heat. It's the energy put into substance to change its form. It's heat we cannot measure. Okay, let me explain. It's if you put a bucket of ice on the stove and you stick a thermometer in it and you keep heating it, the thermometer will not budge from 32 Fahrenheit at atmospheric pressure until the entire ice is melted. So what is happening with all this heat you're putting into the pot? It's probably just used as latent heat to melt the ice. So energy put into a substance to change its form from solid, which is ice, to liquid. Okay, we kept heating that water. It became all liquid. The temperature will increase from 32 all the way to 212, which is the point where the water starts to evaporate. Then it will stop. You cannot heat water more than 212. That's the temperature when it starts to become vapor. So again, substance change form. It's changing from liquid to gas. So you will add heat, but you will not see any temperature increase. So that is latent heat. Adding heat to melt wax, wax giving off heat to solidify. This all like forms of latent heat. So again, take a minute to try to understand what does that mean. Temperature you can measure, and heat that you can measure because it changes temperature, and heat that you cannot measure because it's changing phase. Why is this important again? It's important because this is used on designing an air conditioner. The air has a lot of vapor in it, and it has a lot of latent heat, and there's also something called the dew point. So if you turn on the AC in a humid summer day, the temperature is 90, it's very humid, humidity is 70%, the AC will try to cool the air, but in the beginning it's going to collect all the vapor from the air and turning it into a water and rejecting it outside before we reach the dew point. Until we reach the dew point, there is no increase in sensible heat. You will feel the temperature is the same, but the humidity is decreasing. Once you reach the dew point, which is the point designated by the pressure, by the atmospheric pressure, this is where the water will start to condensate. Then you will start adding some temperature. And again, this is very important because if you design an AC just based on sensible heat, it's not going to work as well, especially in humid areas. So we need to know what is sensible heat and what is latent heat, because that is very important, especially in cooling more than heating. So I hope that makes sense, and I'm going to ask you a few questions. So when you're in the summer time and you're sweating, you know how people always say, oh, this is 90 degrees, but it's dry heat, so it's okay. Why is that? Because if you're in Arizona and you're sweating, your sweat will evaporate right away because it's dry over there, and the evaporation of the sweat will cool your body, so it feels much better. If you're in Florida in the summertime and it's 90 and it's 80% humidity, you will sweat, but your sweat will stay in your body and you will feel your body will not cool off at all. So the sensible heat from your body was used to evaporate the sweat, and that will cool you off. So you are pulling heat out of your body using sweat. That's why dry heat differs than humid heat. So that's an example of why do we need to know about sensible heat and latent heat. Your body can regulate temperature up to 80 degrees by itself, just using the skin surface and ejecting heat into the atmosphere. After 80, you'll start to sweat. If you are not in a dry place and you cannot evaporate that sweat, probably you're going to overheat and you're going to keep sweating. If you don't replenish that water that you're sweating and you don't cool off, your temperature will increase, and eventually it will reach to 100 degrees, and that's when you might faint, because your body will shut down to lower the metabolism. So this is what they actually call a heat stroke. Okay, so please look in the book. There's a few examples, and I hope I was able to explain sensible and latent heat. So again, going back to that and the standard for calibration, we know for sure that the temperature of freezing is 32 at atmospheric pressure, 32 degrees Fahrenheit. Why do I say at atmospheric pressure? Because as the pressure increases, the temperature of freezing will change accordingly. So the pressure does have a strong relationship with temperature. Boiling water is 212 at atmospheric pressure. If you have lower pressure than atmospheric pressure, you can boil water at 210 or 200 if you have lower atmospheric pressure. So if you have a jar and you put some water in it and you evacuate that jar, you make it lower than atmospheric pressure, like a vacuum, you will see it boiling. So water will boil at lower temperature, at lower atmospheric pressure. Make sense? I hope so. At higher pressure, it will take more to boil that water, and it will take more to freeze that water. So pressure has a big relationship with freezing and cooling, and that's what we use for refrigeration. So we use refrigerant to superheat it and subcool it, and probably you will learn about that in principles of refrigeration. Okay, moving on. Enthalpy again, as you can see, it's a measurement of energy. And okay, let's look at that a little bit. So latent heat is the heat absorbed or released when a material changes phase between solid and liquid, or between a liquid and gas. So let's look at that. So we have here steam, so we have water, so subcooled ice. So 32 is the freezing temperature. If you cool it more than that, it's going to be subcooled ice. It's not going to be helpful, just cooling for no reason. Then between 32 and 220 it will melt, and you can see here the amount of energy in the water. So at zero, when the water is solid, there's zero enthalpy, zero energy that's useful to us completely. It's not doing anything for us. We cannot use it to do work. We cannot use it to push an engine. We cannot use it to heat. It's zero. That's for water. As you go up, the enthalpy, which is the energy available to do work, is increasing until we go to 212, and we have 1292 BTU per pound of steam, and that is superheated steam. When you take power plant, you will see that water can be heated to up to 500 degrees, and that will increase the enthalpy. And that will be very useful because the water will have more pressure, more energy, and can do work for us. It can move, steam can move a turbine, it can move a wheel, it can move a piston, so it's very useful to us, unlike regular gases. You cannot use air to move a turbine. So that is kind of an illustration between the temperature relationship to enthalpy and the amount of energy in there. So enthalpy is another name for energy, but for us it's called the useful energy. Useful energy. Okay, writing in the board is not really useful. I learned that. Okay, let's go. Recap, we talked about energy. The first law of thermodynamics. Second law of thermodynamics, heat moves from hot to cold. And if we want to do the opposite, we have to put in equal amount of work. I hope we got that. Latent and sensible heat. Latent heat, heat we cannot measure. Heat that does not change the temperature, and sensible heat is heat that changes the temperature. Latent heat is for phase change or changing a material from one form to another. Sensible heat, it just increases temperature. Enthalpy, useful energy to do work. Few definitions, 5. I hope you can remember them, and they have a lot of applications, and they're all useful, and we need to know these. We don't need to know everything about them from physics science point of view, but we need to know how does this apply to us in HVAC or building management, or building power plants, or building heat, or heat loss, or heat gain. Okay, and I'm gonna repeat those terms a lot, so I hope you, over time, you will understand. Your understanding of these terms will solidify. Okay, moving on. We'll talk about new concepts now. Energy and power, heat and work, pressure versus flow, energy transformation, probably we talked about that a little bit. Energy transport, not transformation, it's transport, how to move energy from one place to another. That's very useful to us. These are the basis for heat system in a house or in a building or any kind of mechanism. And the types of heat flow. So take a second, look at these, try to understand them, and again, probably find more writing about those in the book. Okay, so energy and power. I wish I was in class so I can ask you what do you understand about energy and power, but just to go straight to it, energy is a quantity of something that we can use to do work. It could be chemical energy, potential energy, thermal energy. It's a quantity. How do we use this quantity is power. So energy over time. Think of a piece of coal. What does that mean? A piece of coal is energy, stored energy. When you burn it, you get the power. You release that energy. You can burn it in half an hour, or you can burn it in 15 minutes, depending on how much you fan it. So you can release it quick or fast. So you can get more power or less power over time. Again, think of a gallon of fuel oil and car horsepower and torque. Let's talk about a gallon of fuel oil. So a gallon of fuel oil, we said it has 135,000 BTU. That is energy. If you have a boiler that burns 1 gallon per hour, you will finish that whole gallon in 1 hour, and that's your power. That's the power of that boiler. If it burns 2 gallons, then it has more power because it burns more gallons in 1 hour, which is, again, time over time. I like the car example. I usually use, okay, imagine that you have a Toyota Corolla, 4 cylinders, and you have a Lamborghini, for example. They use the same fuel. The gasoline you buy is the same. But you get, the Corolla will do 40 miles per gallon, and the Lamborghini will use 10 miles per gallon. So which one has more power? They all have the same energy. Let's say they both have the same tank. Let's say they both have 15-gallon tank. You get the same energy. The power, of course, the Lamborghini has more power. It has 600 horsepower, which means how fast that engine can burn that energy and give you power and torque. The Corolla probably is not going to give you as much energy, but again, the 15 gallons will last you way longer than the Lamborghini or whatever V8 or V12 engine you have. So I hope that kind of makes sense. The energy is the same, the gasoline is the same, but how you spend it is what we call power in this kind of terminology. Okay. Work and heat. Work needs displacement. To do work, you need to move one thing from another. That's work. When the piston moves from bottom to top, it did some work. Movement. So work has to do with displacement and movement. And power is how we spend that energy to do work or produce heat. So an engine power in the car, the engine's power is based on how much displacement it does, how much work, how much torque it gives you. That's how we measure that engine power. How do we measure the boiler power? The boiler is not doing displacement per se. It's moving water, yes, but it's making heat. So we're also spending the energy inside the fuel to make heat. So it has more power and less power. So power produces work or heat, and that terminology is what we need to know for our field. The other concept that I want to talk about, and you might want to take a pause and look back at the PowerPoint, but I'm going to keep going, is pressure and flow. So flow is continuous movement of substance or energy through a medium. So water in a pipe, that's flow. Current in a wire, that's flow. We're flowing water through a pipe. In current, we're moving electrical energy through a wire, or heat through substance. These are all flow. There's flow of energy through a medium. Water flowing through energy, we're moving potential kinetic energy through a pipe. Current in a wire, we're moving charges and electricity through a wire. Heat through a substance, we're moving a lot of heat through material, like be it a pan, a rod, steel pipe. If you want to heat it, and it will keep moving heat and it will keep dissipating. In a radiator, that's again heat moving through a substance. So flow buildup, it creates pressure. Interesting. So if we have pressure for water, if we shut the pressure should be constant. If we choke the flow, we will have more pressure. If you have smaller pipe in the water, you have choked the flow, and by doing so, you had pressure buildup to a limit, of course, which is whatever water pressure you have in the house. Current in a wire, if you put big resistance on a wire, you are actually choking the flow, and you will consume a lot of the current. Heat, again, you can put an insulator in a heat, and you basically get heat buildup, and there's no more flow. So flow leads to equilibrium and no pressure, and we always want things to keep moving. Everything wants to be at balance, and everything wants to go through equilibrium. So if you have a balloon, the balloon is under pressure because the pressure inside the balloon is more than the atmospheric pressure. If you poke a hole in that balloon, it will go into equilibrium. Everything wants to go into equilibrium. Everything wants to be at balance. That's the law of nature, and eventually the whole universe actually is going into balance. It's balancing itself. And there's another concept also about entropy, which I don't want to get into, but there's also a destruction of energy, which is very small, and that happens over time. But let's just focus on equilibrium now and energy balance. If you have a tank that is elevated, it have a lot of energy in it, it wants to be equal with gravity. So if you poke a hole in it, it will flow. The water on top of the hills would like to flow back to the sea to be at equilibrium. And this is the law of nature. Energy again, transformation. We talked about energy transformation half an hour ago. That energy transformed from one form to another, from fossil fuel to heat, from heat to mechanical, and so on. That's the transformation. What about transport? Again, transport is moving heat from one place to another, and for that we need a medium. And we talked about that in the previous slide. That you need the medium to transfer energy from one place to another. So I'll give an example about transformation. That's how we transform in energy in the car from hydrocarbon, which is chemical energy, into heat in the engine that move the pistons, and the pistons connect to the crankshaft, and the crankshaft will move the wheels and the axles, and that's mechanical power. So that's a transformation of energy. You agree? And then we transport that energy from mechanical from the piston, that's the beginning of the transformation, to a shaft, to a transmission, axles and wheels. And this is so transport and transformation of energy. It's a different thing. And believe it or not, every time you do a transformation, there are some losses. You are never going to transfer 100% of what you put in. This is like the law of nature. There's no 100% transformation. There's always losses. So you're going to lose here, you're going to lose here, you will lose here, here, and here. So when you do a transformation, you lose. When you do transport, you also lose. Of course, you would like to minimize that loss, but there's always some losses. And believe it or not, based on this example, the car, the regular gasoline car, internal combustion engine efficiency is 35%. Based on the hydrocarbon you put in it to the wheels, 35% of what you put in there becomes mechanical power and movement, and that is very, very low. So that's also an area of improvement. So it's just good to have these concepts, these ideas. For residential heating, we also want to think about that. Probably if you buy a new AC now, it has better efficiency than the old ones because scientists, engineers, and technicians been working on these kind of concepts to reduce these little losses along the way and try to conserve whatever energy we put in. So that is that. Recap. So we talked about energy and power, heat and work, pressure versus flow, energy transformation, energy transport, and types of heat flow. That's next. We'll do that. I know it's a lot of concepts. Please pause and try to wrap your head around this. It's very important, very essential, and I'll use these terminologies a lot. Heat flow. Do I have that? Types of heat flow. How does heat flow? I don't know if I put it there. I think it's in the last slide. I think it's there. That's going to be the next slide. Heat flow. How does heat flow from one place to another? We'll explain that a little bit more. Give me a second. So the new concept going to be in the upcoming slide is heat transport. We did that. Human comfort, climate. What is the difference between climate and weather? Temperature around us, humidity, energy for home use, combustion heating, and electric resistance heating and refrigeration cycle. These are new concepts that we are going to cover throughout the semester. And let's see, I think for this class I will be glad just to do the heat transport. It's here. Okay, heat transport. I think that slide was in the wrong place. Okay. Heat transport, we said heat is energy. Energy transport from high to low. We would say that. Think of the billiard balls. I like that a little terminology. So when you hit the cue ball and the balls hit each other, as they collide, they do transfer energy from one ball to another, starting from your arm to the stick, the cue ball, and the other balls. They just keep pushing each other. On a molecular level, it's almost the same. If you heat a substance, you are heating the molecules, and imagine those are little spheres, and they keep moving faster and faster, and they hit each other. Once they hit each other, they transport the energy from one molecule to the other. Does that make sense? I hope so. So let's look and see if I did that. So smaller balls, if one hit the other, this one will hit this one. And if you think of energy as pushing that ball and hit the other one, every time it hit the other ball, it will transfer some of its kinetic energy, but also there is some losses. The harder you hit the first ball, the more the second ball will move. So thinking about that concept, if you hit something solid, solid means that the molecules are very close to each other. So the transport of energy is going to be very close. If you have three balls next to each other and you hit them, probably the energy will transport to all of them almost the same. It's faster. Meanwhile, if there's more space, you're going to hit one, the other one will go, and you might miss it. It will take less energy to transfer the energy in this ball to the other one. If you have gas and you have more sparse balls, again, you're going to hit this one, it might go over here, and not hit any of these, and hit another one over here. So think of molecules as like a pool, tables, balls, and if they are very close to each other, that's solid. As they go a little bit further, it's liquid. If it goes very, very sparse, they are kind of gaseous. So there are three means of heat transport: convection, conduction, and radiation. So convection, let me see if I have that. Yeah, okay. So conduction happens, it's heat transfer through direct contact with material. That means it's in solid. Conduction happens in solids. Okay. So if you're heating a pan, that's solid completely, so that's conduction. It's very simple. If you're heating anything solid, you are conducting heat. Convection is heat transfer through a fluid movement. By fluid, I mean either gas or liquid. And so that's convection. So it requires not solid, it requires liquid, it requires fluid, which could be either gas or liquid, air or water. That's an example. There's subdivision of convection. There's something that's called natural convection, which is also called free convection, and it's buoyancy driven, meaning that hot air will rise, it cools off and falls. So if you have a heater with no fan or anything, it will heat the entire room using natural convection because the air will move by itself. If you put a thermal camera, you'll see the air heated, rising and coming back, and that is natural convection. And it also happens with water, natural convection. What is forced convection then? That's when you use mechanical means to move the air. You want to make it faster, so you are transporting heat using convection, using a fan, a pump, whatever you have. That is forced. It has mechanical means. And I will repeat that a lot, just so we understand it as we go along, how to distinguish between conduction, convection, and radiation. So radiation has nothing to do with the substance. It does not need a medium to go. It does not need solid. It does not need liquid. It just goes through even vacuum. The sun is radiating heat to us through vacuum of space. It's basically electromagnetic waves produced by heat. So it comes by anything. Regular lights, animals, we are radiating right now based on our temperature. If you look at infrared camera, probably you will see the heat we are radiating. It has nothing to do with the medium, with the air. What about LED lights? That's a very interesting question, just came to me. What does that do with anything? LED lights, usually they're very, very cool. And the reason they really do not consume a lot of energy is because they're not making any heat. So the energy consumed by LEDs is mainly used to make light and not heat. So they don't radiate as much as incandescent lights or fluorescent. So radiation, it's a big spectrum. I think I have a picture of that here. Yeah. So that's the electromagnetic spectrum. And every wave in the world is a sinusoidal wave here. And based on the frequency, which is how many wavelengths do we have in 1 second. So speed of light or the wavelength. This is the wavelength, is from tip to tip. So the more frequency we have in 1 second, the more we have different kind of waves. So let's look at that over here. For light, for visible light, we have ultraviolet and we have infrared, and this is our visible light. This is what we're getting from the sun right here. But sometimes we get other stuff as well. So after ultraviolet, there's nothing but X-rays and gamma rays. This is the sunlight here. That's the part that gives us heat, infrared. The ultraviolet actually you do not see, but it gives you cancer. And if you go with higher X-rays, you can see through flesh, then it becomes radioactive. So this is radiation. So radiation is a wave. How is this wave being made? It's those electrons vibrating very fast, and by doing so they emit light, and sometimes they emit a wave. It's the frequency of the electrons vibrating in that nucleus. So thinking about that, what about radioactive? Why do you think it vibrates so much? What is the material that we use for radioactive sources? Plutonium and such, and those things are radioactive because these substances radiate so much that they even glow without even being activated. So again, it depends on the material itself that make that vibration. Okay, enough for that. It's a lot of science. So back to the sun again. How hot is the sun? It's around 10,000 degrees Fahrenheit. 49% of the sun energy comes from Earth, solar heat. That's just heat. 46 is light, and 5% is UV radiation. That's really interesting to know. We need the ozone layer to protect us from some of the UV and the gamma rays, because there is some of that. So yeah, be careful, use sunbathers. The sun gets closer and further again during the seasons, so that's why it gets hotter and cooler. And we also need to know about reflection and absorption. I don't know how to say that. Absorbance. So absorbance is how much you absorb heat and reflect. Dark color usually absorb more heat, and light colors reflect more heat. And again, light colors emits also more heat. So this is all pertaining radiation. And why am I spending a lot of time on radiation? Because we're going to use that in HVAC. There's a lot of heating means that use radiation. We can also use radiant floor heating, and that's also radiation. And there's also some heat emitters that you can put in the ceiling to heat the space. Some information here that helps. Again, human comfort. We would like to be in 65 to 85 degrees Fahrenheit. That is in terms of temperature. Thermal equilibrium, again, temperature will move from hot to cold. We want to always go to equilibrium. So if you put a hot object and a cold object, eventually they will equalize. Body metabolism will produce heat. Depending on your body metabolism, some people are hotter than others and produce more heat, but and it also depends on the diet and the location and a lot of things and what activity you're doing. So your body is metabolizing the food to make heat, so your body is producing heat. We produce heat as a human body on average about 85 watts, so like a light bulb in a way. Airflow has also some contribution to heat, because if we just remember a few minutes ago we talked about convection, so airflow is a good means to transport heat. I'm throwing a lot of information at you here. What is D temperature? That degree day temperature, which in some books is the design temperature for a dwelling, but it has to do with the location. So in Springfield, for example, the design degree temperature is 0. We design for the coldest day of the year when we're doing heating system. We're doing cooling, we design for the hottest day of the year, and this information is available usually online and you can find in your H22 book. Humidity, another concept, is the amount of water in the air. I talked about it recently when we talked about latent and sensible heat. It's measured. So relative humidity measures how saturated the air is with water vapor. Up to 100%, you can have 100% humidity. And if you look at your weather app, probably tells you 50 and feels like 70. So that has to do with the relative humidity and how much you can evaporate. It measures how rapidly sweat can evaporate from the skin. Humid air contains more heat than drier air. Good fact to remember. And that's why also it feels hotter when you are in Florida or a place that has a lot of humidity. Humid air feels better in the throat and lungs, in the lung system. Should fix that, lung system. And so that's why we don't want to be in a completely dry climate. In the winter, you need to put a humidifier because we want that range. So we want to be between 40% and 60% humidity. That's our comfort level of heat. Warmer air can hold more moisture than cooler, and the fact that it's very important to remember. It works very well for drying stuff. Relative humidity, RH, depends on rainfall, closeness to a body of water, clouds, winds. Indoor humidity depends on temperature and air intake from the outside. So there's a lot. The source of humidity is water. So if you live close to water, if you have a lot of water sources in your house, probably you'll have a lot of humidity in that area, and we'll talk about that as well. So we prefer to have less than 60% humidity and more than 40, so between 60 and 40% relative humidity. So again, since this is the first chapter, we'll talk about all these things we talked about later in the semester. But how do we control all that? Giving the human comfort, giving the need for heating and cooling in a house. What are our means to make heat? Either combustion for heat, we're burning fuel, we're burning oil, we're burning gas, we're burning wood, or we can use electrical heat, which is basically using electrical coils to heat water and air, or we can use a refrigeration cycle, which can be used for heating and cooling as well. It's called a heat pump. So these are the means we have so far to heat or control temperature and humidity in buildings. So as a recap, I know I threw a lot of material on you. We talked about heat transport, that's conduction, convection, and radiation. We talked about comfort, human comfort, and that is temperature between 65 to 85, and humidity, that's temperature, RH, from 40 to 60, and temperature around us, what does it matter? Humidity, what kind of energy use for home, and we talked about combustion heating, and electrical resistant heating, also to heat a house, and finally the refrigeration cycle. So I think with this I will conclude my comments on this PowerPoint. I will post the PowerPoint on Blackboard, and please try to read the book, and if any of these concepts do not make sense, especially with latent and sensible heat, please let me know, and see you in the class. Okay, bye.